of course, this central tendency and this particular shape of distribution was noted by many scientists before, and many scientists tried to describe this shape analytically. And one of the first who actually got a description, analytical description, was a German mathematician Carl Friedrich Gauss. And therefore, we know this distribution also as a Gaussian distribution. So normal distribution and Gaussian distribution are kind of synonyms. And then this is the analytical expression for this distribution. It looks a little bit complicated, especially if you don't like math, but we will discuss this formula in detail. So what this formula shows you, it shows you a density of a particular value x, for example, height of person, which is a function of many different things. But if you look at this, you will find out that, for example, this is 2 pi, it's constant, right? E is constant, right? 2 is constant. Then you will find out that actually, besides x, you also have 2 parameters of this function, which is sigma and mu. So density depends on 3 things. It depends on 2 parameters, which are mu and sigma, and it depends on the particular value, of course. Right? So let's discuss this function in detail. So first of all, let me make a simplification, because parameters, let's fix parameters. So sigma and mu are fixed. In this case, this does not contain x, right? So it will be also a fixed value. So let me replace this with just a letter a. So when I write a, I simply mean this 1 over sigma square root of 2 pi, okay? And then another simplification, you can see a little negative here. So negative power means 1 over the same, but in the power, in the positive power. So e in negative something, it's the same as 1 divided to e in positive something. And that's exactly what I also use here. So now this is a little bit simplified way. I also noted that mu and sigma are parameters. You can see them in red. And x is a particular value. Now let's think a little bit about this function, how it should look like if you make a plot. Of course, I'm not going to make a detailed plot, but let's try to just to guess, okay? So let's consider 3 different situations. The first situation when x is equal to mu. So imagine that this is x, so let's say mu is located somewhere here. So this is exactly x is equal to mu. So what if x is equal to one of these parameters? What if x is equal to mu? So in this case, apparently x minus mu will be 0, right? So this will be 0. And therefore, all this will be also 0. E in the power of 0 is 1. Anything in the power of 0 is 1. 1 divided to 1 is 1. So in this case, f, so the density will be equal to a, right? So if I make, for example, this is density, and this is where we have a. So this is where we have the density, right? For this particular case. So let's consider another situation when x is much larger than mu. For example, x is equal to, I don't know, mu times 2, mu times 20, and so on and so forth. What happens in this case? In this case, x minus mu will be a positive number, very positive, right? Because x is much larger than mu. So it means that when you square it, it will be even larger number. And then by dividing to 2 sigma squared, you kind of compensate it. You make it a little bit smaller, but still it will be large. And then e in the power of large number will be also a large number. And when you take 1 and divide to any large number, I don't know, 10 million, for example, right? Then you will have a very small number, right? So it means that the more far x go from mu, the smaller and smaller and smaller density will be. And then somewhere very far away, the density will be almost 0, right? But on the other hand, we know that it's exponential decay. So we can make this exponential decay like this, right? So the more far we go, and then it will approximate. It will never reach 0, but will become very, very close to 0. Now let's consider the situation when x is much smaller than mu. In this case, x minus mu will be a small number, right? It will be a negative number, actually, because it's smaller than mu. But you see, we have this little square here. So it means that this squared and this squared are the same values. So if you have, I don't know, 12 minus 2 squared, or for example, 2 minus 12 squared, it's the same value, right? So therefore, the distribution will be absolutely symmetric around mu. So you will have the same decay here. Of course, I cannot make it absolutely symmetric, but that's the overall idea, right? So two things. First of all, it's symmetric distribution. Second, mu is where the density is the highest. So this is exactly the most expected value. So mu is the most expected value. And then the more far you go from mu, the less and less and less density is. So density gets smaller and smaller and smaller and smaller. And it means that chance to get a value also gets smaller, right? So now let's talk a little bit more about these two parameters, mu and sigma, with a couple of extra examples. So let's start with mu. So what you see here, you see two populations. I use height of people as just an example, as a simple example. In this population, you can see the mu is 160 centimeters and sigma is 10. We don't know what sigma is, but I just set sigma to 10 in this case. And in this population, mu is 180 and sigma is also 10. So we didn't change sigma, we changed only mu. And then I made these theoretical functions. As you can see, the functions are identical. The shape is the same. What is different, it's the position of this peak. So here, the position of the peak is exactly where you have the mu, 160. And here, the position of the peak, exactly where you have 180, right? So this shows you once again that the meaning of mu. Mu is the value where you have the highest density. And it means it's the most expected value. So it means that the values around mu is, this area around mu, a small area around mu, it's the most crowded. That's the meaning of the density. So it's most dense. And then you can see these two distributions together. So you can see again that shape is the same, the width, the shape is the same, everything is the same. The only difference is the position of these centers. So the red distribution is kind of shifted by 20 centimeters related to the blue one, right? So mu is expected value. It's center of your distribution. It's the point where the distribution has the highest density. We are talking about normal distribution, of course. Now let's talk about the meaning of sigma. So in this case, you also see two populations, but the mu is the same. You can see 170 here and 170 here, and you can see that the position of the peaks is the same as 170. However, now I changed the sigma. So sigma is equal to 6 in this case, and sigma is equal to 12 in this case. And now you see the meaning of sigma. The sigma makes your distribution kind of flatter, but also it makes it wider. So the variation of the values which have non-zero density or not very small density, so to speak, is much larger in case of the red curve compared to the blue curve. Moreover, you can see that the variation is actually, if you think about kind of values where the density gets really, really small, you will find out that this variation is exactly twice larger, and sigma is also twice larger. So sigma, the meaning of sigma is following. Look at this one. It compensates the distance between x and mu, right? So it kind of, if x minus mu is equal to 10, for example, x minus mu is equal to 10, and sigma is 5, then this ratio x minus mu divided to sigma, and then you can square afterwards, will be 2, right? But if sigma is 10, then this ratio will be 1, right? So you kind of change the density. You kind of compensate this distance between x and mu by setting sigma a little bit larger. So sigma, it's a measure of variability of your values. The larger sigma is, the larger variability is. So it means that it's likely that values can go far from the mu. And this is just an example where we have both distributions together again. So you can see it. So here we have sigma equal to 6. And here we have sigma equal to 12. So sigma, it's a parameter of normal distribution that defines its variability. It defines how far values can go from mu. Now let's talk a little bit more about the meaning of sigma and the distances. So what you see here, I took two values. So this value is exactly by 1 sigma smaller than mu. And this value is exactly by 1 sigma larger than mu. So we take an interval plus minus 1 sigma around mu. Let's look and let's try to calculate density for this interval. So apparently when x is equal to mu minus sigma, so this is this one, right? So in this case, x minus mu will be equal to minus sigma, right? You simply subtract mu from here and mu minus sigma will be minus sigma. But then you remember you square it, so minus sigma squared will be sigma squared. So what you will have E sigma squared divided to 2 sigma squared. Or you will have E 1.5, or it will be square root of E, right? So this is what you will have in the denominator here. And therefore the density will be equal to A divided to square root of E. This is just a short version of this. What if x is equal m mu plus sigma? So in this case, mu plus sigma minus mu, so x minus mu will be sigma. And again, if you square it, it will be sigma squared. So it means that the density will be absolutely the same. It will be A divided to square root of E, right? So this is the density. So this is A divided to square root of E. And this is also A divided to square root of E, right? So you can see that you have, this is A, you remember? So this one is by 1 square root of E smaller than A. So if you go by 1 sigma, you have by 1 square root of E smaller density. Okay, what else we can do? We can actually compute integral under this curve where x goes from this to this, right? And then we will have this area. You remember integral on the curve, it's area, right? If you compute this integral, you will find out that this integral is equal to 0.683. What's the meaning of this? You remember that the total area under PDF curve is 1. It means all values, right? So the area under this curve shows you the probability to get a value between this and this. So it means that probability to get a value x, which is 1 sigma away from mu in both directions, is exactly 0.683. Or, in other way, 68.3% of all values in our population lie within 1 sigma from mu, so lie in this interval, right? So if you think about, for example, you have population with mu equal to 170 and sigma equal to 10, so it means that if you take mu plus minus sigma, which is 170 plus minus 10, or from 160 to 180 interval, right? You know that 68.3% of all people in your population have height between these two values, okay? Between 1 sigma around mu. Okay. Now, if you take 2 sigma, so you can see that now I have mu minus 2 sigma minus plus 2 sigma, so the interval is twice larger. But what happens with the densities, right? So again, this is mu minus 2 sigma. We compute this distance, x minus mu. It will be minus 2 sigma. And if you square it, it will be 4 sigma squared. Right? If you take mu plus 2 sigma, this one, then it will be the same. It will be 2 sigma. The distance is 2 sigma. So this distance is simply 2 sigma. And this distance is also 2 sigma, right? And then if you square this distance, it will be also 4 sigma squared. And then you have like E, you have 4 sigma squared here and 2 sigma squared here. You can see this is 2 sigma squared. So it means it will be E in the power of 2. So that's exactly what we have here. Of course, it's 1 divided to this, right? So it means that this density is E A divided to A squared. While if you take 1 sigma, this one, it will be A divided to square root of E, right? So you can see a very big reduction of density when you go from 1 sigma to 2 sigma. Okay. Then you can also see that the density gets really, really small here. Again, if we do this trick and compute area between mu minus 2 sigma and mu plus 2 sigma, then we will get 955. So again, it means that the probability to find a value within 2 sigma around mu is 0.955, or 95.5% of all values lie within 2 sigma from mu. Okay. If we take the same example, mu is 170, we talk about people, height of people, sigma is 10, then mu plus minus 2 sigma will be 150 and 190, and you know that 95.5% of all people in this population will have height between 150 centimeters and 190 centimeters. Okay. Finally, if you repeat this with 3 sigma, you can see that it gets very, very small. So this is 3 sigma. The density is almost 0, right? The density is almost 0. And then if you compute the integral, you will find out that the area under this curve between mu minus 3 sigma and mu plus 3 sigma, it's 997. So it means that 99.7%, almost all values in your population lie within 3 sigma, plus minus 3 sigma. So sometimes it's called 6 sigma rule. So it means that in this, you remember that this is 3 sigma, right? And this is also 3 sigma. So together it's 6 sigma. 6 sigma. So almost all values lie within this range of 6 sigma around mu. Okay. And then you know that if it's 997 inside, then on both tails you have 0.015 and 0.015 because it's 1 minus 0.997, which is 0.003. And then you have to divide it to 2 because you have equal portion on each tail, right? So you can see that this is a very, very small value. This is a very, very small value. You still have it. It's still possible, but it's very unlikely. Okay. You can think about this as, for example, density of population. What you see on this picture, it's a density of population around Paris, the capital of France. And then you can see that this is the highest density, so it's a city center. And then the more far you go from the city center, the less and less and less population density is. So it's still possible to find a person here or here because you still the non-zero population, non-zero density, right? But the highest density, the highest chance to find a person is exactly in the middle. Okay. These 3 numbers are very important for understanding normal distribution, and for using normal distribution, I recommend you to remember this by heart. So sometimes it's called a rule of 68, 99, 95, 99. Although it's not exactly 68, 95, 99. So if you go 1 sigma away from mu, you will have 68.3% of the values. If you go 2 sigma away from mu, you will get 95.5% values, all these values in this interval. And then if you go 3 sigma, then you will get 99.7. You can see these numbers are not nice numbers, right? You have a lot of decimals. So if we think about some nice number, for example, 95%. So in this case, 95% is a little bit smaller than that. So it means you need to go a little bit less than 2 sigma away. And that's exactly 196. So if you want to get exactly 95% of most common values, which lie around mu, you need to take 196 sigma away from mu in both directions. We will actually prove this experimentally also in this learning sequence. And most of the values lie within 3 sigma of mu, around mu, right? So the values outside this range, 3 sigma range, are very unlikely. We will call them also extreme because if you observe them, especially in a small sample, then it's kind of unlikely event, it's extreme value, and you need to pay a special attention to this value, why you got it. Okay. In the next video, we will talk a little bit more about mu and sigma. We will give them a particular name and also learn how to compute these 2 parameters.